Yeah.
Here's another card that's from Tiffany.
Okay.
Sorry. You the guy in charge.
Collector.
Collector. Magic science.
Yeah. Okay. Oh, right here.
Please.
Sure.
Where are we? Okay, Jeff said he would be here.
Okay.
Yeah.
Jeff tomorrow at lunch.
Oh, perfect.
And it's
Not sure about that, but
Then who else is there?
how many do
So
we have?
is
Two more,
Julia
right?
still here? Or
Who?
oh, Julia.
Julia.
Mhm.
And then
Let the microphone go.
and then also this. Julia, did you see my email about how we're gonna run this?
I sort of know.
I was busy lecturing at the time.
So, the idea is I think.
Do we just have one microphone? The other one didn't work?
They're worried about echo from the
Oh.
two microphones.
Okay, welcome back. We're going to end this week and the other weeks, the following weeks, with kind of discussion of what we've learned over the past week. And to get things going, we're going to ask the lecturers to kind of just remind us briefly of what they covered, and hopefully that'll jog some questions in your mind. And then we'll open it up to just free-for-all questions. So let's see, Grisha, why don't you start?
Okay. Fluid mechanics is many things for many people. I hope you understand it. So engineer, mathematician, physicist, biologist, zoologist, they see the same flowing fluids in a very different light. So what I try to convey is that a physicist viewpoint, and it's very necessarily hugely oversimplified. And even in physics, there are different degrees of oversimplification, and I am almost at the far end of simple-mindedness. And I hope that you really take it in mind when you think about these lectures. And the way I see fluid mechanics is, first of all, in this physicist way of seeing two things at a time and not more. So for me, fluid mechanics is a competition between inertia and friction. Okay, that's essentially the story for me. There are two protagonists in the story, and of course, in any mechanics, there is always inertia and friction, but it's trivial for mechanics of bodies, right? There's inertia keeps the motion and friction stops the motion. And continuous medium, and that's what fluid mechanics is. It's mechanics, but it's continuous mechanics. And here, interplay of two pretty trivial and innocent factors getting very, very non-trivial, right? So you have an ideal fluid. The moment it flows near a solid body, there is a little friction over there. It could be very little friction, but the world with a little friction is very different from the world with no friction at all. Okay, so it starts producing vorticity, and it's a nonlinear system. This vorticity is getting carried away somewhere. It changes life completely. Okay, that's the way I want you to see this story. And of course, there are very fancy different ways when physicists, and we use a lot of terminology, you know, like symmetries, anomalies, this and that. But essentially, it's always, at least in my mind, I'm trying to identify these two things and how they actually interact. Okay, and fluid mechanics for me, it's inertia versus friction. And if I would ask myself what I want see from you, I'm 64, right? this Beatles age where it's just the only thing that I expect you to feed me. And you will be doing fluid mechanics 20, 30 years from now. So I want you doing fluid mechanics different than we did, right? And it's always very natural feeling of every generation, and I will do it differently. My feeling is that maybe your generation would push it more towards things which will be more about information than about energy. My teachers were obsessed by the way that bodies resist motion, how we burn energy, how much trillions we need to spend, you know, to move this gas from this place to that place. And now I think we're more and more interested in how do we control these things, right? Because fluids are very easily non-equilibrium. Non-equilibrium means lower entropy. Lower entropy means more information, where this information is encoded. I very much hope that you would push in this direction, but I will be happy to be surprised and see absolutely unexpected directions in which you would push it. That's my 5 minutes. Thank you.
Yeah, so one of the things we wanted to achieve in this first week was to provide kind of an overview of things that we'll be looking at more detail in the subsequent weeks. And although Jim Sauls wasn't able to join us, I think that Julia's talks really filled in and introduced us to the soft matter aspect, active matter aspect, so that we had this whole range of scales. And since Professor Srinivasan isn't here, maybe I'll just say a couple things about his 2 talks. The first one you'll recall was about quantum turbulence, and he was thinking particularly about helium. And the main conclusion, I think, from his talk was that at larger scales, it looks a lot like classical turbulence, even though at small scales, we see these quantized vortices. I was left with a question about why the vortices tend to group together in the same polarity. It's something that I hope to learn more about. And maybe if Jim Sauls joins us later in the school, we'll hear more about that. Srini also talked about the sun. And so going sort of at an opposite extreme scale, although we're going to go to even larger scales later on in the school. And the most surprising thing to me was his conclusion that the convective zone of the sun was nearly exactly stably, just neutrally stratified, which runs counter to the sort of pictures that one has of that being this kind of continuously convecting region. So that seems to have a lot of implications if that result holds up for various models of the sun. And since Grisha mentioned something about his hopes for you, maybe I'll just say that one hope I have is that maybe some of you will use understanding or inspiration from this school to think about solving this colossal problem facing humanity of climate change. And so Tiffany's talks gave us a setting for that, and we're going to be exploring that a little bit more in the subsequent weeks. So let me turn this over to Tiffany.
Thanks, Brad. Yeah, so I saw my job this week as to introduce you to the notion that climate change is a physics problem. So lecture 1 was laying that foundation and connecting to the atmosphere in particular as a fluid and the fundamental role in the stratification. And then these equations, leading more explanation, emergent structures we see, the jet streams, the Hadley cell, and coordinates. Mentioned at the beginning, this was all sort of chosen in a way to culminate in the 3rd lecture, where this very important problem about how do we understand what is the focused on those that we understand best. Obviously, this is a summer school after all, but unwrapping the time dimension, the spatial dimension, impacts of extremes, and all of that, I think, is ripe ground to cover. Some of you also asked about machine learning, and I think the great experiment there in this realm of the physics that we have to represent on small scales, so convection, radiation, there's a lot of hope that these algorithms can help us better represent these physical processes within our global model. And then I think one thing that I see coming down the pipe too is how are we going to get ourselves out of this problem if we keep behaving badly? What is the role for physicists in thinking about so-called geoengineering and so on? Okay, we have to be at the table, okay, because I think this is unfortunately might be the route we need to take. So with that, yeah, happy to hear questions.
I came here to ask questions, not answer them. But I guess I can just very briefly say, my background in fluid mechanics, I'm a very pure physicist, and like Grisha, I love to look at very idealized problems where, very basic field theory and things like that, statistical mechanics kinds of approaches, you can make good progress. Connecting that to reality is exciting, but it's sort of beyond my level of expertise, but I'm always looking to learn more. Let's see. I've worked with oceanographers who do, NASA has these beautiful satellite images of the ocean surface and things like that. And there's remarkable, surface waves, internal gravity waves, vortical flows, obviously, that you can track using passive tracers like algae blooms and things like that. Beautiful, beautiful imagery that in some cases you can actually pull out, spectra of ocean waves and things like that agree phenomenally well, and perhaps surprisingly well with some very idealized sorts of theories. So I think that's enough of me.
Okay, well, I hope you can remember what I was saying because it wasn't very long ago. So let me go back to the beginning and try and say where I hope this field might be going. I've told you about active turbulence, and that's a central bit of the field, but there are lots of other things as well. One thing which was interesting is understanding this active self-assembly and using active matter as machines. And this is perhaps as much an engineering as a chemistry problem as a physics problem. But in the end, it would be nice to be able to use this stuff. There's been loads of work about trying to make tiny robots, tiny active particles. Very nice, but they haven't really taken off yet. Who's going to have the big idea so that these are starting to be used all over the place? Biology, that's when I stopped doing the sort of generic stuff and went more towards a research thing. That was my ideas on how one might move on biology. And I think this is a really exciting area, but we have to be careful. There's a lot of biology that isn't physics. Can we be helpful? How much can we explain? But then we have to leave things to the biologists because molecular mechanisms are important as well. And so putting those two things together is an exciting sort of challenge. One of the other thing was that this is non-equilibrium statistical physics. And a lot of people do work where they're looking at much simpler models than the one I was, where they can start to solve them properly. Things like the equation of state don't work. Things like detailed balance don't work. What is there to replace them? So there's lots to do there. And in the particular active turbulence stuff, we were looking at, a lot of you said, can we make a theory which starts from the topological defects? I mean, I've explained what happens. I told you we understand what's happened. We don't have a theory. And it would be really nice to have a proper theory of this stuff, a predictive theory. So it's up to you guys to do that. And I also want to say thank you very much for all the questions. It's lovely lecturing when people ask questions. It really makes it worth it. Thanks.
Thank you. I would second that. It was a real treat and pleasure to have an audience that was so enthusiastic and asking so many interesting and well-placed questions. If I could review the content of my lectures, it would be, I think, to say that when you think about fluid dynamics and you think about solving these problems, we're very rarely, particularly computationally, but also theoretically, we're very rarely thinking about one set of equations, right? There's not just the Navier-Stokes equations, because we have to think about, especially if you want to do computation, a direct attack on those kinds of equations at the scale of, say, the Earth will remain undoable for a long time. And so it's really worth thinking about what we can do to ensure that we think about the right equations to solve. And then hopefully I gave you some ideas of what the right tools are to solve those equations and what it looks like, both in terms of the practical, like actually just doing simulations and keeping track of all of the ones you do, particularly when they're very large, but also the sort of like ensuring that the model that you're doing makes sense and that you have a tool that you can use to check that. So that's kind of what I would do. I would say it's very nice, and I think that I was able to present to you a tool that we've built over a long time, but it's not the last tool that should be built. And I hope that some among you will figure out a better way to solve these problems, and even maybe faster or more efficient, really, I think it'd be the thing I would hope to see going forwards.
And perhaps some of you will start using Daedalus during the remainder of the school and help solve a problem that you're working on. Leo, do you have anything you want to add, or Jeff?
Well, I'll just say it's been a pleasure hosting you guys here for the first week, and I'm really impressed by how energized and how you are with questions and discussions. And I visited the poster session last night, and it was really just unbelievable, despite all the heat and a little bit of hiccups there, and constrained by our physical space. There was no even hint of that hindering anybody's discussions. People were sweaty and screaming and waving their hands, and it was just really wonderful. So I'm really hats off to you, and I hope you keep up this energy for the next 3 weeks. I'll refrain getting into the physics. We have plenty of experts here, although I've done my share of hydrodynamics. I haven't been doing it recently, so I'll hand it over to Jeff.
One theme I noticed throughout this week, and I probably noticed it because it's my own passion, is how fluids self-organize. And it's not brand new, but Grisha's story about von Karman, was it, who, when he saw structure, assumed that something must be forcing it. And so, went to great lengths to remove any possible source. But what we see is in wakes and in the sun and in the climate system and in active matter, that the fluids all on their own self-organize to do really interesting and exciting things, and things that impact us. And one of the things that physics really brings to bear is thinking about the forces and thinking about how organization happens. Tiffany did a really nice job of showing how we use those kinds of idealized arguments to get ideas about what kinds of structures we see in the climate system. And I think that carries across all fluids.
I should add that we are going to make some changes for the subsequent poster sessions. We're going to use both rooms up on the top floor, the library, so help reduce the volume. And we'll try to make sure the doors are open. So I can't guarantee the stairwell door will be open, but we wanted to, I guess, open it up to questions at this point. And I think this is being recorded, right? So maybe I'm going to pass around the microphone to you, and then we'll bring it back to the panel.
Or you
want to?
Yeah, or the question could be repeated by the person.
Yeah. Okay. Maybe we should do that.
So it would be with this summer school being getting, I guess, connections between the
looking for when we're trying to find hydrodynamic analogs between these very different systems? Might be a very general question. Anybody?
Okay, maybe I'll take a first stab and then pass around. So the question is, what are we looking for if we're exploring connections between quantum fluids or quantum mechanics, maybe even, and classical fluids? And I think that there are connections can be made at many different levels. So we heard about a direct connection with the superfluid helium this week, and we may hear more about that. And we also have a couple other speakers. Dan Sun from Chicago, who's been thinking about this a lot, Jim Sauls, if he comes, possibly Alan Dorsey. So I think there's more to come on that. But next week, we'll have Antoine Vinay, who will talk about topology in certain fluids, rotating fluids, and which was directly inspired by discoveries that were first made in the quantum context. So that's making an identification at the level of waves, the Schrödinger equations wave-like. So that's more of a mathematical mapping than a physical mapping. Does anyone else, Grisha?
Couple of words, yeah. That's why I think that fluid mechanics is a place where we meet each other. For example, I meet high energy physicists and they tell me that quark gluon plasma is essentially ideal fluid. And then, meteorologists can meet with solid state physicists. And every phenomenon we're talking about, from black holes, currents, other physics, magnetism, etc., they are very different. So in a sense, when you ask what is the fluid mechanical aspect of it, I would define it as a collective aspect of it. Essentially, fluid mechanics is the simplest way of looking into things from a very large distance. Not much looking into details. And when you look from a large distance, the main thing that you notice is the conservation laws, how it's actually transported, etc. This essentially is the language, because the moment that I will try to understand what actually happens with heavy ion collisions, it's a lot of things happen. But when a friend of mine tells me that you see that there is such a strong interaction, that viscosity is so small that it's like ideal fluid, and this is this jet and that jet, at least I understand the aspect of it, okay? So what I think is, and that's why I think it's very good that you learn in fluid mechanics, you will be able to talk to absolutely different people. You'll be able to talk to engineer, you'll be able to talk to mathematician, and to physicists from very distant way of life. It's just macroscopic view.
Yeah, so maybe I'll echo what Grisha said. Hydrodynamics is about conservation laws, but also about broken symmetry. So if you have a broken symmetry, particular continuous symmetry, then that's another mode that you have to consider that's going to survive at long scales, because there are Goldstone modes associated with it. And I would say almost by definition, quantum mechanics, maybe Grisha will correct me or others will correct me, plays little role in it. It does determine the microscopic. It's the microscopic that determines the parameters that enter the equations, and perhaps in some systems you can even predict those parameters being exactly zero, being quantized. But other than that, by virtue of looking at long scales, where the only thing that survives are conservation laws and broken symmetries, you kind of well outside of the realm of sort of the microscopic physics, and that's the beauty of it, and that's why we can make any kind of progress, because that's where you take advantage of universality, and that's why, as Grisha said, different fields can talk to each other about similar phenomena, different physical phenomena, but same mathematical behavior.
One of the conservation laws, one of the symmetries that's been mentioned that is really prevalent in fluids is this particle relabeling symmetry. And that, plays out in many different ways across all these different systems and results in a conservation of vorticity. And so, that plays a role in the stuff that Srini talked about the first day, the liquid helium vortices, vortices on the sun, vortices in the atmosphere and ocean, vortices on Jupiter. I really wanted to do some vortex analysis of some of the pictures that Julia showed this morning. And I think vorticity is one of the things that ties it all together, in my view.
try that. Who had a question back here?
Thanks for that question. It's something I've been thinking about too, and so I'm glad you brought it up. But so I've seen that like experimentally, there have been a lot of analogous experiments, like you said, for, I don't know, surface waves as an analogy to black holes. But I also know that on the theoretical end, there has been work that I don't know if it's still happening, but there was a period in which people were trying to connect Einstein's equations of gravity to Navier-Stokes and going both ways. But the thing, I do see a lot of similarities, and I agree it's interesting to look at physics and hydrodynamics across scales and the universality, but more specifically, how much can we say is, okay, we see a similarity across scales, but that this physics is the same? Like, how much can we say, oh, we see this in an analogous system, then this teaches us about what it means in the respective one, right? So, what can we learn from doing an analogous classical experiment to a quantum system that we can't learn from just doing the quantum experiment, or vice versa with going into cosmology or something like that? And similarly in theory, what can we learn from solving Navier-Stokes that can teach us about solving equations in another scale? I don't know if you have any comments on that.
Grisha, you raised your hand.
Finally, you want to know how to make a discovery. Look how it was made before, not this way. Okay, so and just as a way of let me tell you a short story about my teacher. My teacher, I actually had two, one Russian, one American. And my American teacher, Robert Kreitman, was the last assistant of Einstein, and he came from MIT at 49 and guess 50, and he started to work with Einstein on a general field theory, which was the way around quantum field theory. And the idea of Einstein was, there is a very classical nonlinear field which is called fluid. So maybe let's spend a year or two and go understand it, because it creates this interesting fluctuation. It's kind of create fluctuation in statistics by itself. And so that Kreitman about 51 went into doing turbulence theory, and he stayed there for 40 years, never coming back to quantum world. That's life. Don't look for general lessons. So I was fortunate to meet him there in the classical world, because I always hated H-bar. I still do.
One of the things I think we can learn from each other, one of the reasons why I really like this kind of a school is first of all, you don't want to reinvent the wheel, and whether that applies to using Daedalus instead of writing code from scratch, to thinking about vorticity, or thinking about what kinds of experiments to do, what you expect to see. The mathematics, to the degree that the mathematics is similar, we can learn from each other. But I think what also happens is that in different fields, our attention is on different sides of what are sometimes the same problem. And so we learn different pieces. We see this a lot in the climate system, in the atmosphere and ocean. For a long time, meteorology and oceanography were very separate fields. They lived in different departments. And still there's enough of a separation that sometimes things are done first in oceanography, and then the atmospheric scientists adopt them. Sometimes the atmospheric scientists do it first. Probably the biggest thing that is like this, I would say, is Lorentz's discovery of chaos in thinking about meteorology, which has, changed the way we think about modern science in all fields. So that's the benefit. That's the hope, is that it's easier for me to sit in a lecture on active matter than to think of the ideas myself. Although the translation problem is challenging.
I'm no expert on the mapping between general relativity, black hole horizons, and fluid mechanics, but I did see a simulation, I think, of a black hole merger that was done at Caltech that showed similarities to the inverse cascade. And what struck me was how viscous it was. It was sort of inherently very highly damped. So in some ways, it has a connection closer to soft matter, even though it's this giant, astrophysical scale thing, than it would to high Reynolds number flows, or maybe it has, maybe the electron fluid is a closer connection. Does anyone down here want to say something?
Just to flag up this idea of topological defects, which are all over the place. I mean, certainly in the early universe, strings, which form patterns very like these 3D topological defects in liquid crystals, are thought to be important, not active ones, but passive ones. And of course, you've got topological defects in quantum systems, I think, yeah? And lots in passive liquid crystals all over the place. And understanding how the physics there maps onto each other is another, perhaps a useful way to go.
I guess the question came up about, superfluids and things like that. So I have a little bit of background there. So I thought I'd make a few comments. I think helium-4 was first proposed because viscosity is identically zero, right? Maybe it might be a shortcut to very high Reynolds number turbulence in a finite cell. But the only way you get a vorticity, right, is if you have vortex lines. And so there's this interesting communication where, yes, I think to some extent that turned out to be true. Helium turbulence looks very classical, but why that's so led to some very, very deep questions in terms of helium cryostats and stuff like that. So how do these vortex tangle dynamics work to give you effectively the Navier-Stokes equation on large scales? There's this beautiful communication between fundamental quantum simulations, whatever, of vortex lines and Kolmogorov 5/3 laws and things like that. And I guess I have a background in critical phenomena as well. That's from my PhD work and things like that. And so I told you, I guess Rossby waves are my favorite wave, but helium-4 is my favorite element by far. So, fluctuations on all scales, right? When you look at phase transitions in Ising magnets or anything like that, there's this critical point where you have fluctuations across all scales and power laws and things like that. And so there is, to some extent, this beautiful analogy with turbulence Grisha mentioned, right, where you have this cascade, energy cascade through the inertial range, and there is, if you work hard enough, there is indeed an inertial range where you get this more or less constant stream of energy coming down the scales that doesn't care about the fact that there's viscosity as long as you keep the scales separated enough. But I've attempted. It's a much more difficult problem, right? You can try to develop renormalization group theories and things like that. They've been dismal failures for turbulence, absolutely dismal failures. And some of my work is basically proving that. Much more difficult, although there are lots and lots of analogies with field theories and things like that. So it's not so much, I think, that, oh, great, we can simulate the early universe in helium. I'm not sure how well that works, but what I find fascinating is that it opens up whole new questions, right? That if you observe this kind of phenomenon in helium, maybe it has some connection to fluid dynamics, but it leads to whole new sets of questions about the microscopics of the quantum mechanics that you never would have thought of before. So.
I guess I had a follow-up to what you said. You said that renormalization group theories are failures in turbulence. And I was wondering if you could expand a bit more on that as to why. Yeah.
I've worked on it 40 years, and part of it was really great scientist, Sasha Knowledge. They always ask me every time, why do you even expect?
Well, here's the point, right? Is that there's this wonderful development that eventually led basically to, a Nobel Prize in 1981 or thereabouts, right? So this is, I had arrived at Cornell, and then Kenneth Wilson got the Nobel Prize for the normalization group. The reason that worked out so well is that 3 dimensions is not too far from 4 dimensions. And so you have this epsilon expansion, it's 1, but 1 is small enough that 1 squared is still much smaller than anyway. But so there's this wonderful epsilon expansion that basically allows you to solve everything. You can get 3 or 4 decimal places on the critical exponents for the Ising model and all these things like that. It's just amazing how well it works. Historically, there was an effort to try to find an epsilon type expansion for turbulence, but what you find then is that epsilon has to be 4. And in fact, the theory around which you try to expand turns out to have the cascade in the wrong direction. So you get a theory with an infrared fixed point, so large scale, you get small scale fluctuations, but looking to large scales. Turbulence is the opposite way. You've got non-universal stuff happening at large scales that eventually leads to sort of universal stuff going in the opposite direction. So it's an ultraviolet fixed point. And so if you try to do this epsilon expansion, in fact, at epsilon equals 3, it flips from infrared to ultraviolet. So your fixed point completely changes. It's just, they have nothing to do with each other whatsoever. So that's some of the technical level, and nobody's managed to fix that.
Because first of all, I mean, this is what Peter says is kind of a background. Let me give you a little bit as a evidence from a person who failed at least 4 times doing this. So I think that it counts for something. I see there is an inverse cascade. So you can try to do it inverse cascade. That's actually what we started to do. We say, okay, it's the wrong way of direct cascade. Let's do it for 2D inverse cascade. Does not work out. Well, it will someday. First of all, what you realize is the main difficulty is not even perturbations. You can always find the parameter to it. It's that you're working with non-equilibrium. So what Wilson did, he took a Gibbs distribution and renormalized it. He knew the form of distribution, and it was completely formulated in terms of single time values. Okay, so Gibbs distribution, that's the beauty of thermal equilibrium. Probability of any configuration does not depend on the way it was created. That's a fundamental thing. You have detailed balance. Now, it's maybe complicated to renormalize this probability distribution, but at least you are working on a time slice, right? Nothing like this ever is possible, even in simple non-equilibrium system, okay? So you need to work really with the statistics, which includes temporal evolution. You need to describe the whole statistics. There is no time slice. Okay, you say, then you can do it in the spirit of mass theory, trying to renormalize currents of probability, not the probability distribution, but the current of it. And that's what actually several people trying to do, and it's very complicated because there are no general rules. Equilibrium, it's always Gibbs. It's just a question of what is in the exponent. Okay, so it's a pretty complicated. It's in your generation, it probably will be done, but it will be done in a different way. Okay, you'll be working with dynamical perturbation theory and a system with, if you want to do it for turbulence, with very many degrees of dynamical freedom. Okay, that's a big deal.
Thank you. My question was regarding the differences between weather prediction and climate prediction. So it seems like the fact that weather is a chaotic system prevents long-term reliable estimation of weather. But still we are able to make seemingly concrete statements about extremely long-term consequences in terms of climate. Now the fact that climate is, in a naive sense, a time average of weather, does that allow us to do this? Or, I mean, what is the reason why, which allows us to make a definite prediction about a seemingly chaotic system?
So yeah, that's a very good question. But I think we have to understand the different setups of the problem, right? So the weather forecasting problem comes down mostly to an initial value problem, right? So that's the issue, and we get the deterministic chaos and so on and so forth. But I guess a good interpolation point between weather and climate projections of CO2 is the seasonal cycle, right? So I always know that winter, as long as I'm away from the equator, will be colder than summer. And so why do I know that? Of course, it's from the forcing itself, the evolution of Earth around the sun. And so the forcing can basically dictate a solution beyond the sort of sensitive dependence on initial conditions. But there's timescales over which these overlap. And one of the issues with the noise that I've talked about, trying to get away from the noise, is that there's noise on decadal timescales due to the atmosphere and ocean coupling. And so that has shown to be quite important, actually, when you sort of integrate your solution for the climate problem. You have to be mindful of sort of what part of the decadal variability you find yourself. So part of how you can get out of that is just to force the system with a larger, CO2 increase. But yeah, it's a very good question.
Traditionally, there's a distinction between weather and climate. Weather is day to day, and climate is some long-term average. The canonical time scale is, say, 30 years. But it's becoming increasingly clear that there are these lower frequency variability. The one that is most famous is El Nino, and one major effort is to try to predict climate on the decadal time scale, and they're predicting El Nino is part of the key to that. And we still don't quite know how to do it, but El Nino, I think, brings in unpredictability on the decadal time scale. One of the questions about climate is Arctic sea ice. When is Arctic sea ice going to disappear? And one of the tools that's I think is really amazing, and we haven't, the climate community has really been using it a lot, are initial condition ensembles. And so you don't just run one climate model, you run an ensemble of 30, 50, I think Max Planck is up to 100 different ensembles, and they only differ in their initial condition by machine level round-off error. And when you do that, for instance, and you look at the sea ice, loss of sea ice, that you've got the date for the loss of Arctic sea ice varies by decades, I think, and the ones that start out losing sea ice first aren't the ones that end up ice-free the soonest. So there's a lot of unpredictability on a variety of timescales. And so, your question in the framework of the classical view of weather is short-term and climate is long-term, you would say weather is an initial value problem and climate is a boundary value problem. But that separation is not quite as clean as we would like.
So both Brad and Tiffany mentioned that you're hoping that more physicists could contribute to address the challenge of climate change. And I'm wondering, what could physicists help in this regard, and what problems could we help to address? And specifically for someone like myself as a condensed matter physicist, what could we do?
Yeah, I mean, there's no shortage, I think. I guess it depends on, I've had a few people ask me about, examples of people who've made that transition. I think what's really nice is there are people who've done that. Certainly from high energy, we get a lot of people. So condensed matter, maybe I can't speak specifically to, but there's a lot of problems, particularly related to convection and the smaller scale physics that could benefit, I think, from people from condensed matter. And so that's an effort that has been advertised even in physics today. There's a nice article that's been written about some of the problems that would benefit more people joining along. Yeah. Certainly, I think, as I've described, the sort of the higher order moments of what's going to happen in the extremes is really important. That's where most of the impact is felt. If you look at socioeconomic impacts, damages, so more investment there. But yeah, I can perhaps provide some of these sort of perspective pieces that people have written with more concrete problems within the Slack channel. But yeah, there's no shortage. The key is, I think, to find, like you're saying, the skills that you have that would best translate into the problems and the myriad of problems that we have to address.
I would answer, well, first of all, that many climate scientists like Tiffany self-identify as physicists, as just they may not be in physics departments. But if we're sort of thinking about physicists in the traditional fields of condensed matter physics or high energy physics, then I think that there are insights that they have that they can bring to climate science. And I would include also experimental physicists in that, because there's a whole range of experimental techniques that could be applied to better observing the climate system, better characterizing it. So for instance, just recently, the APS released a report on monitoring methane emissions, and it called for the development of high quantum efficiency photon detectors so that the spectra from methane can be better quantified from satellites. So there's some real hardcore experimental work that needs to be done, improving that, and also improving the spectra, understanding the spectra of methane in the atmosphere. So there's some theoretical modeling there too. But then there's ideas like Peter has investigated in applying equilibrium statistical mechanics ideas when there are systems that have a large timescale separation, which can lead to insight into vortex formation, for instance. And so that might not occur to somebody working in an atmospheric science department. Maybe it would, but coming from this statistical mechanics perspective. So I think there's actually many different, I could imagine many different ways that physicists in the future might contribute. Does anyone else want to say something?
Our field is highly collaborative, and I think there are a lot of opportunities for people to from outside the field to do postdocs in climate science. NCAR, which is the lab up the hill here, they've got an advanced study program that hires postdocs every year, and they explicitly have a mission to broaden the field and to hire postdocs from outside the field. That's how I got into climate science. My PhD was in theoretical physics, and then I went to NCAR. I think the GFDL, that's the Princeton lab, their postdoc program brings people in from outside. And so that's sort of a natural point in your career if you're interested, is you're bringing all these skills. You've got strong experimental skills, strong computational skills, strong theoretical skills, maybe all of them. And those are all needed in our field. The one caveat I would say is the stereotype of the physicist who comes into a field and thinks they can solve it in a year or two. But then, that's okay, right? I mean, Krejcinen got sucked in and spent 40 years and made amazing contributions. So a little bit of humbleness is needed, but there are lots of opportunities in that sense. And working with people who are already in the field is a good way to jumpstart a new direction.
Yeah, thank you. I have a question about the scientific computation and the theory. And I know from Jeffrey that Daedalus was developed by a group of young, passionate scientists who have their theoretical background and they have their scientific questions. And nowadays, I know it's super hard to balance between theoretical research and coding. That's at least that's for my PhD. I found it hard to balance between the two. One is to make the tools. The other is to develop the theory. So do you have any insight on, or could you tell us more about Daedalus and how you all guys got the idea to make it and how you make it to the current state? Thank you.
Okay, so to directly answer your question, I think that the fundamental way we do science is broken. We have no mechanism to adequately fund or sustain the kind of work that needs to be done in computation that I can see, at least certainly in physics and in applied math and in theory. So Daedalus has never been, with the exception of a $60,000 grant from the Australian government, Daedalus has never had any funding at all. It's always been funded entirely by volunteering. So I don't really have any good insights other than, this is something that there's been a lot of people who have thought about, obviously, and as software writ large becomes more and more a part of doing science, that question I think is going to be come more and more important. I don't know the answer to that. And to answer your question about like what lesson can you learn from the success, what success Daedalus has had, I think that was, am I paraphrasing you correctly? Yeah, I think honestly it was luck. Like the science that we've done with it has been sufficient to acquire funding that has allowed us to continue to have careers in science, which is how we've been able to continue to do it. That's not guaranteed. And I don't have any good insight, unfortunately, but I do think that it's a problem. And I think that's something that could continue to become a problem as we increasingly rely on tools. This is, of course, not true universally, right? I think obviously there's a lot of sustained effort for things like global climate models and things. It's not every part of science, but certainly in like the sort of more theoretical areas in particular that I'm familiar with, it's just not something that I think the community is fully equipped to deal with.
Maybe I'll just add that there's a very ambitious effort to write a climate model from scratch in the Julia programming language, and that effort is largely privately funded. Governments aren't supporting it, and there's several existing or many existing climate models. Most of them are written in Fortran, and so this group has decided to use modern software techniques, programming techniques. And I think it's very exciting myself. There's a question over here.
Thank you. A few of you have mentioned non-equilibrium statistic mechanics. I guess my question is, as someone who doesn't know anything about it, where should I go and start learning about it? The other thing is, I don't think we've seen much of that in the lectures yet. So I'm wondering if you could give some more concrete examples to help me see if it's a completely different approach or if it's something that we could incorporate into this macroscopic view that we've talked about with some extra terms or something like that.
So you've come to the right place, because we're going to have some talks about just that in the next few weeks. But does anyone else want to say something? Jeff?
Well, perhaps you could mention who's going to speak on that. I think Freddie Boucher probably will say something about that. He's going to talk about extreme events. I think it's very much cutting edge. I think the physics community has made a lot of progress in a particular corner of non-equilibrium statistical mechanics, referred to as stochastic thermodynamics. And so that's a buzzword that you can look up, and there's a lot of review articles on that. I've done a little bit of work trying to see whether stochastic thermodynamics is useful for climate science. I think the jury is still out. I should say that there was just last month, maybe, a really nice article in Reviews of Modern Physics. The authors are Morgan O'Neill and I don't know who the other author was, Martin Singh, on second law of thermodynamics in the climate system. It's a really, really nice review article that clarifies a lot of things. But I think in general, that's one of the things that is on the horizon. And there's a lot of interesting work to be done. And that's one of the places that physicists, I think, can play a big role. I think it's also an example where the problems of different fields let you focus on different things. For instance, a lot of the stochastic thermodynamics has been focused on steady states. And one of the things I'm particularly interested in is not so much a steady state. The thing about the climate system, and we almost always average over the seasonal cycle, but it's really a periodic steady state, a cyclostationary state. And the question of what are the non-equilibrium statistical mechanics of such a cyclostrophic state, a cyclostationary state, I think are really interesting. And then, of course, there's not just the annual cycle, there's the diurnal cycle. And so those are different questions than that people who are doing the similar kind of theory to different physical systems will ask different questions. And it's putting that all together, I think, that leads to progress.
Yeah, so Fred Boucher will be here talking about large theory, which he has sort of two thrusts. He'll probably tell an analytic to various to use it as a way to access. Otherwise, because they might be a very long thing that maybe you know. One on equilibrium StatMech. The other, another thing called something I work him on, which is basically along the lines of the closed summation that Tiffany discussed, but done more systematic to try to and other non in cases which are very much out of equilibrium and may not be either.
In 2019, I think there was a special issue of the Journal of Statistical Physics on non-equilibrium and climate, I believe, and I'll put that in the Slack.
So just the question of, where you learn about non-equilibrium statistical mechanics. All of these fluid equations, including the Navier-Stokes equations, are non-equilibrium statistical mechanics, right? That little nu, right, is a thermodynamic quantity. There are microscopic definitions for it as in terms of equilibrium correlation functions, right? So, Onsager, relations and things like that. So these you can look up in textbooks. Knowing this doesn't help you solve the Navier-Stokes equation. But then as you move further and further away from equilibrium, I'm not sure you even call that non-equilibrium statistical mechanics. I mean, it depends on your definitions, right? So you can move away from linear response, right, and get into much more complicated territory. And I think Freddie Boucher is one of the people who does this sort of thing. So you can look up classic non-equilibrium statistical mechanics in textbooks. So.
Thank you.
So I'm from physics department, and as we have learned in this school, we see fluid dynamics across different scales, and also from Professor Falkovich's lectures, we can learn a lot of physics from fluid dynamics. But interestingly, in my school, fluid dynamics is not a standard course. I don't know if this is a common phenomena or it's because my school is strange. But well, that's probably a comment or a question. And I have a kind of a second question is that, so I'm working on condensed matter system, and it seems, okay, now it seems that in condensed matter physics, the electron is an important object. So can we learn anything from fluid dynamics or hydrodynamics for electrons? So this may be related to my first comment.
Yeah, sadly, it's not uncommon in the United States. But Julia, maybe since you come from a department that has a lot of, it's physics department that has fluid dynamics, do you have anything you want to say before I turn it over to Grisha?
In Oxford, certainly when I was an undergraduate, you didn't have fluid mechanics in physics. It was either engineering or it was maths. And it's still a little bit like that, I think, although it's starting to change. Certainly it's not one of the courses our undergraduates have to take. And on the whole, they don't like it because it's a bit messy. It's not absolutely laid out in a line which starts at the beginning of a calculation and ends up at the end. So they're a bit worried about it. Once they take it, they enjoy it. So I think it is not traditionally a physics subject, except in Cambridge. I mean, damped is, except in Cambridge.
It's something which I've actually talked with Kreitman that in America somehow it's applied math or engineering. I'm very happy to see you from different countries because it's your generation. I very much hope that would create more or less an international culture in this respect. Because when I grew up, everything was very clear. Physics is what physicists do. And if it's written in Landau Lifshitz, then it's physics. Okay? And the volume 6 of Landau Lifshitz is fluid mechanics. End of story. Okay? Now, what with Brad, we organize physics of climate. You remember? Not Aspen, but Santa Barbara. And David Gross, Nobel laureate, who was a director at KTP, we were kind of all there. The people who were studying forest fires, you know, oceans. And David asked, who studied electrodynamics by Jackson? And there were like 2/3 people raised up. Okay, so it does not matter whether you're archaeologist or what, you studied electrodynamics by Jackson, which is definition of physicist. What is important here? He did not ask, did you study fluid mechanics by what? Bachelor or Landau Lifshitz or whatever, classical textbook on fluid mechanics. I think it's a deficiency of American system. It's now slowly improving, and I very much hope that your generation would help it to see that fluid mechanics will be part of physics. Electrons help a lot. It's good now that electrons start, you know, making vortices and waves. And now can these people say, well, okay, let's read Landau Lifshitz or bachelor textbook or even LAMP. Some people know the really great textbook. So it's all for you guys to improve. Feynman was a true physicist. But notice, Feynman's lectures aren't for physicists. Meditate on this fact. Feynman lectures on physics aren't written and delivered for physicists. They're popular lecture for non-physicists. Because we all learn physics from this lecture, right? But it's something about culture in this.
So my own physics department was a leader in the field of acoustics. But then when Sputnik went up, everything changed and the department, you know, moved into so-called modern physics, and there was no more acoustics hired, and that generation just faded away. So there was a kind of conscious decision, I think, to allow or move fluid mechanics into these other departments. I have a funny story about those fire ecologists at the KITP. They were listening to all these physics talks, and one of them came up to me and he said, I keep on hearing F equals MA, F equals MA. What is this F equals MA? So I told this to David Gross, and he said, who is that? I want to know, but I refused to tell. Any other questions?
Thank you. On another subject that's not taught to physicists, information theory is something you kind of mentioned, Professor Falkovich, as something that can be used in the future to develop advances in hydrodynamics. Now, I know very little about information theory. Can you tell me why you think this is something that can be applied to this area, and what has been done in terms of concrete problem solving that can be used to shed insight into hydrodynamic problems?
Recorded. As the lady over there asked about non-equilibrium, okay, so equilibrium is a maximum of entropy, okay? Let's keep an energy of a system, okay? Let's deviate it from equilibrium. What happens? Entropy goes down. What is entropy? Entropy is a measure of indeterminacy, is a lack of information about the system. So the moment you deviate system from equilibrium, you learn something about it because entropy is less, right? This is a new perspective on all this stuff, because before we asked ourselves how much energy we need to spend to deviate system, to pump the fluid, right? This is a deviation from equilibrium. And I think that also, because now we are more kind of focusing on how to control things, then the information is now a very practical matter. And when you, so I wrote this book on fluid mechanics. It's a course I taught 20 years ago. I'm now teaching last 8 years information theory, and next year I'll publish a textbook on information theory. I think it's a natural evolution, okay? And in the other hand, just a short story about, I was a department head of a complex system, and we had 3 departments in physics. And so we had this room for students, and each department was given 2 formulas to write. Like, you can write 2 formulas, and there will be 6 formulas, most important formulas in physics. Okay, and I made a mistake. I wrote S equal to logarithm gamma. Now I would write F equal to E minus TS. I think the statistical physics is probably the main thing that physics contributed just to mankind. Okay, and this is essentially information. And when you look at people who study black hole entropy, self-driving car, brain research, active inference, they all write E minus TS. You would not believe it. Any image, artificial intelligence, all optimization schemes, they use the same thing, okay? It's time we start speaking the same language, and we learn a lot from each other, okay? Maybe one more thing. Arnold said, physicists see analogies between phenomena. Mathematicians see analogies between analogies, okay? So start seeing analogies between analogies. It's much more interesting, right? That's what information theory is.
Anyone else? Take that one. Okay. Any other questions?
So I have another question about Daedalus. So I'm curious if you're looking into implementing anything that's currently being researched in numerical analysis, say to solve more complicated geometries or like certain complex forcing in fluid problems. And then I'm also curious how you evaluate the performance of Daedalus, I guess with respect to how it meets the needs of the overall fluid mechanics community.
So the answer to the first question is, I don't think that's the way exactly we would characterize it. In other words, there's not like a particular numerical analysis thing we're doing motivated by a particular fluid thing. I think just to follow on this idea of I'll give the applied mathematician's answer, right? Which is that we've been really, we found it very fruitful to think about the analogies between analogies, right? So if a Chebyshev T and a Chebyshev U are related in some way, well, it turns out that they're both can be related to the ultraspherical polynomials, and the ultraspherical polynomials can be related to the Jacobi polynomials. And it turns out that when you're there, then you can come back to the Legendre polynomials, and that helps you in the sphere. So what we've been working on a lot is trying to think about generalization and what kinds of ways we can generalize these things and think about the algebraic structure that underlies these classes of classical orthogonal polynomials that have been known since time immemorial, sort of, right? So I think we are thinking about these kinds of things, and we're thinking about them in terms of, so of course the big thing is, can we do spectrally accurate things on arbitrary geometries without having to do something like the way it's currently done, like spectral element methods, where you're kind of like blocking together things? And the answer is probably yes. But whether or not it's practical is a question. So that's something that we're thinking about. I'm sorry, what was the second part of your question? How we evaluate? Oh yeah, that's a really insightful question. We ask our friends. Like I want to maybe underline the fact that this is like really 5 people who don't. All of us have jobs doing something else, teaching, research on whatever it is we use it for. So I think it's maybe much smaller in enterprise than maybe that you might think it to be. So that's really something you're asking the exact right question, right? Which is that the question we typically tend to answer in high performance computing is how many stage cycles per CPU second can we get? And that's nice, right? That's a good benchmark because we don't want to be wasting resources. But at the same time, the real benchmark is how much science can we get done per dollar spent on this technology? And I don't know. I mean, that's kind of an economics question, I guess, at some level. But in terms of meeting the needs, it's really something we try to, like, whenever we talk to people, well, is this something that could be useful for your problem? Is there something that we can do that might help you see a generalization or exploit a generalization, right? Like, oh, I have a code that solves this equation, but it's really hard to add a term or make it into that equation. Is there some way we can sort of help with that? So I think that's kind of the way we think about it. But I would love to think more formally about answering the question that you asked, which is, I think, really the right question. And I don't know, honestly, the answer. The other thing, of course, is that we always measure the metrics that are easiest to measure. This causes some problems in society, generally, right? But we are always looking for our keys under the lamppost.
Let me ask you a completely unfair question. Do you think we'll ever have a FFT for spherical harmonics?
Yes, I do.
Right, great.
So there is already a fast transform for spherical harmonics. I unfortunately cannot remember the author's name. It's someone in a math department in Canada. I'll put the reference in. And I believe it's n log n. The problem is, algorithmically, we always think of asymptotics, right? Unfortunately, in reality, there's a prefactor, and the prefactor is currently very large. Whether or not it will become practical, I don't know. But I hope so.
Well, for Professor Ruiz, actually, I would like you to discuss a little bit on something that I was a few years ago in a summer school for numerical methods to fluid mechanics. Different people talking about different methods. And what we see some groups doing sometimes is like modifying the problem to fit the limitations of the method instead of properly choosing the method for the problem. I think there's a little bit of like you quite get passionated by your own method, so you try to use it. I would like you to discuss a little bit on it and discuss what limitations and how it can like drags the evolution of the field forward, please.
Yeah, I mean, every tool is a hammer, right? Like, part of the problem, I think, is very often, particularly until recently, and by recently, I mean maybe the last decade or so much high performance computing or scientific computing was so locally grown that if you came up somewhere where there was a tool that existed to solve a similar problem, you'd use that because that's what you knew about. It's a problem of information, right? But I think that's still a real challenge. I think that's a real problem that we often face. But I'm not sure exactly what the right answer is, other than to try to make sure that you research the problem that you're solving rather than the method that you have available to you, especially now as there are more and more open source tools. This is why I think open source is really important. It's not just some philosophical distaste for closedness, though I think that like the auditability of code should kind of be a big part of what we do is in science. I think the bigger point is that it allows you to discover, oh, well, there's actually something, if you want to study a hypersonic turbulence, you probably should not be using Daedalus, right? Because you have shock waves distributed all over the place, and there's methods that are much better suited for that. So I think it is something to think about, and I think the question should always be how does this solve your problem? But again, part of our motivation in developing it in the first place was actually the reverse, watching people solve problems in subsonic turbulence using codes that were developed for nuclear weapons research, which is basically like gigantic blast waves, right? This is extremely inefficient and in fact makes problems. I think the story of algorithms is that you'd rather have today's algorithms on yesterday's computer than vice versa, because algorithms can beat Moore's law easily. So I think that's a really important point to keep in mind.
Thank you. I got a question especially for Tiffany and Jeffrey. So when we want to predict climate and weather, it seems that our models become more complex and complex over time. And the question I would ask now is, do you see any place nowadays for simplified models, like, for example, Rayleigh-Bénard convection? And what do you think can we learn from that for our predictions or for the models that we need?
Yeah, I mean, I hope, maybe I won't speak maybe specifically to Rayleigh-Bénard convection, but I hope my third lecture illustrate and Manabe's work himself, illustrated the value of simple models, of stripping away physical complexity to reveal the essential physics governing some kind of emergent pattern or response. And so, you have to, I think it's guided by what we see emerge from the complicated numerical simulations. That's why I don't want to throw them out with the bathwater. I think they tell us something very important. Amongst the complexity, there's emergent simplicity in some of their responses. And so it's those responses that I think that we tackle then to understand, what is the physics of them. So in the context of convection, one of the emergent responses that is very much of a target in the field is the so-called convective aggregation. And this is the idea that actually emerged from convection resolving models, where in periodic domains in this radiative convective equilibrium, what they find is convection tends to form these patterns of all of the upward motion in one part of the domain and downward motion everywhere else. And the relevance of this to convection in the real world and manifestations of large-scale organization in the real world is really exciting. Surely maybe Rayleigh-Bénard has something to say, but I think what my lectures also showed is you have to treat moisture. So that would be the direction to go. You have to kind of know which direction to go, I think, amongst all the complexity.
Sorry, I know you meant the other Jeffrey, but I just wanted to point out quickly that Jeff Fallis wrote a really nice review, I think, in Proceedings of the Royal Society on exactly this topic. I'll put it in the Slack, but he brings up exactly this point, and he's actually done quite a lot of work himself on moisture in Rayleigh-Bénard, which along with Steve Tobias will be here later. And so I think there's really quite a lot of nice things to be done there.
I think one of the things that has become more explicit in the last decade, say, in our community is to really emphasize the model hierarchy that Tiffany, I think, did a really nice job. And choosing which levels, I think you should always be thinking about multiple levels of this model hierarchy, and choosing which levels to ask particular problems is really important. And at the simplest level, it goes back to which two things do you want to include? And I think Rayleigh-Bénard is perhaps less apt. Well, I think we've learned a lot from Rayleigh-Bénard, but the drawback, I think, of Rayleigh-Bénard is the boundary condition, the upper boundary condition. In my thinking, I think the atmosphere cools through radiation, and that's a different boundary condition. And there's been a number of people who've been working on simplified convective models with radiation or with moisture, Rayleigh-Bénard convection. But by themselves, it's not enough. I think the hierarchy from the kind of theoretical analysis that Tiffany, Tiffany's lectures kind of encompass that whole model hierarchy in a very short time. And that I think is really the way forward. And we of course want to run more expensive models. There's always stuff that is parameterized that if only we had bigger computers, we would be able to do explicitly. Climate models have some processes that we know the physics of, but we just can't afford to do them. They have some processes that we don't understand. Biosphere, atmosphere interactions. We don't have equations for tropical rainforests. But there's still a lot of value in the simplified end of the model hierarchy. It requires a little bit more creativity and wisdom to create those models. It's easy to rely on the same simplified models that have been relied on for the last 50 years. but there's a lot of people doing interesting things. And I think that's a place where, again, the physicists can play a role. I mean, physics is looking at the real world and pulling out of that the essential features that you can then say something theoretically about. And that results then in the simplified piece of the model hierarchy.
So for the most part, all of you have talked about solving ODEs and PDEs, but as a condensed matter theorist, I've often encountered methods like Monte Carlo or stellar automata. What role do you see these two methods, for instance, playing a role in solving hydrodynamic problems?
Who would like to take that question?
I'd stick my neck out and say I don't think Monte Carlo is going to be very useful because it doesn't have the right dynamics. Cellular automata can have the right dynamics because you can put in conservation of momentum, and that's what underlaid the development of lattice-Boltzmann methods, which are a nice way of solving Navier-Stokes-like problems. I mean, there are lots of other nice ways as well, but it was a nice idea that cellular automata, where you conserve mass and momentum and just get the symmetry right, gives you in the continuum limit the Navier-Stokes equations. So then you go on to molecular dynamics, and that is useful, but probably not at large enough lengths and timescales even for Navier-Stokes of complex fluids.
I can make one comment, right? So I've worked on equilibrium statistical mechanics theories of Jupiter's red spot, basically. How do you get these steady state patterns? And this is going back more than 30 years now. But you can write down a free energy for the Euler equation. And it's a very complex thing, with vorticity and things like that as the variables. And one of the tools we applied was actually doing Monte Carlo on a distribution of vortices and seeing how do they assemble into a spot-like shape as you change the energy and things like that. So I think that's pretty rare, because I think outside of equilibrium, where you know the probability distribution, it's tough to do it, but that was one example.
We should have a competition about the things you haven't worked on. Who can find the thing you haven't worked on?
Sure. I'm not sure how the phrase Monte Carlo is used in condensed matter physics. But in terms of climate science, one of the state-of-the-art areas that people are actually looking at is Tiffany mentioned that because of our limited resolution, we have these subgrid scale parameterizations. And one of the things that I think is a very exciting development is people doing stochastic parameterization. And that then involves some sort of Monte Carlo sampling on each grid point. And I think the jury's still out as to whether that is an advance or not in climate modeling, but it is something that a number of groups around the world are actively working on.
Cool. Thank you.
So I learned that there are two kinds of chaos. One is like conservative, and I think it was discovered by Poincaré in celestial mechanics. And another one is dissipative, which was Lorentz from fluid dynamics. So does turbulence has any connection with any of this chaos? This might be a big question, but I want to know if any of you have some insights.
You want to take that, Grisha?
Well, the answer is no, but it's a simple answer. Well, chaos and turbulence are very different phenomena. Chaos is essentially something that you have a trivial special structure, but non-trivial temporal evolution. So you have something which are dynamical system, but just because any space larger than 3 degrees of freedom normally developed stochastic attractor. On the other hand, what you will hear next week, or maybe in 2 weeks from Nigel Goldenfield and other people, that on the ways of turbulence, one way is chaos. So you can create just one mode, second mode, third mode, and they start interacting, and you get a temporarily chaotic behavior. And this, when you increase the number of such modes, eventually will come to turbulence. But now what we learned in the last maybe, I don't know, 10 years is that there is a special way of turbulence, for example, in pipe flows, right? Where you have a stable flow and you don't develop instabilities and there are not many modes, but in space, there are regions like puffs of stochastic behavior, and there are some other region of laminar. Still, turbulence, it's when all this come together into many degrees of freedom deviated from equilibrium. So turbulence is stochastic both in space and in time, okay? In this respect, it's like all your chaos multiply by 10 to 23 or whatever, 10 to 11, your favorite macroscopic number. And again, there is something which I really need to warn you that applying stochastic thermodynamics is a beautiful science, and it's essentially the following thing. You have a system in a contact with a thermostat, but it's not in thermal equilibrium. But it's in a contact with a thermostat. Okay, so you have a piece of iron and there is current. It's non-equilibrium, right? But the number of degrees of freedom which are out of equilibrium, stochastic thermodynamics is always very small. I wouldn't say even finite, very small. But it's always stochasticity there from white noise, which made it essentially probabilistically treatable. Turbulence is something where you force system in a very, very non-stochastic way. You drive a car. Depends on what driver you are, you're still not white noise driver, right? And that's a huge difference because now the statistics over which you average comes out of dynamics of your system and nobody knows how to do it. And stochastic thermodynamics is much, much simpler because input statistics there is always white noise, okay? Be careful about it. It's a different phenomenon.
So I'm going to agree and disagree. I agree that chaos is low dimensional. Lorentz discovered chaos by thinking about just 3 modes of the atmosphere, and the chaos is among the amplitudes of those modes, and turbulence is high dimensional. Where I'm going to disagree is that when you take the macro turbulence of the climate system, for reasons that are poorly understood, it seems to self-organize into phenomena that are essentially low dimensional. One example of that is El Nino, where you can apply stochastic thermodynamics precisely because for reasons that we don't understand, it self-organizes into low dimensional dynamics. The noise is the weather. And again, we don't have a theoretical closure that would give us what the noise is, but one can model it empirically. And there's a number of situations like that in the climate system. And for about a decade, there was a lot of fighting in the climate community about whether this made any sense or not. You'd go to meetings and they throw chairs at each other. But at the end of the day, these low dimensional models are skillful in the sense of prediction. And if you go, for instance, to NOAA's El Nino forecast page, they have what are called spaghetti diagrams, which are all the different models that have lines that look like a pile of spaghetti on a plate. And sometimes they agree and you're confident there's an El Nino, and sometimes they disagree. And some of the models that are considered skillful enough to be included in this ensemble of models are these stochastic thermodynamic models.
If you have time scale separation, you can treat part of it as a white noise. That's totally legit.
If you don't know what the El Nino is, I'm pretty sure that Antoine Vanay will tell us about that next week. So, well, I think we've come to the end of our period. So the only thing remaining this week is we'll have the catered dinner at 7 o'clock up in the same space where the posters were. And hopefully we'll be able to get in the building this time. The same way as yesterday. Yeah, whatever way works.
Same way.
All right, well, thank you for all the great questions.